When Cisco split the CCNA program into two separate certifications, the CCENT and CCNA, they really freed themselves up to add a lot more information to what it would be to be a true CCNA. One of the things that they added when they did the split was VPN technology. And this is, from their point of view, I'm sure this was a tough decision because VPNs are one of the things that are overtaking the world. It's a technology that is just becoming more and more popular everywhere you go. However, the complexity of it is enough to fill an entire course. I could talk about VPNs in all their glory, from concepts through configuration, and it would easily take me a series of 30 videos to make that happen. So what they've done when they decided to splice VPNs into the CCNA program is Cisco thought, how about we give just enough to be dangerous? Meaning just enough of the technology, what it is, what it's used for, and how it works to allow you to know what's going on, know what VPNs are all about, know where you would use them, but then leave the configuration to elsewhere. Thankfully, you know what the Cisco SDM is, a graphic interface. One of the major reasons Cisco released the SDM for their routers was because of VPN connections. To set them up from the command line, it is so tedious and it can take so long and have so much troubleshooting. They just said, let's just make a wizard to do it. And they did. So most of the individuals that set up VPNs nowadays on Cisco routers and PIX firewalls use graphic interfaces to do it. Even myself, I will throw myself right out there. When push comes to shove, I will reach for that GUI immediately because VPNs are a pain to configure. But I get too deep already. This is what we're going to talk about as we work through this video. Let's talk about what are VPNs. First and foremost, for you acronym junkies, VPN stands for Virtual Private Network. It is a network that is virtually private, not really private. And therein lies the whole concept of a VPN. Everybody has an internet connection. We have them from home. We have them at our offices. Even if our office has private lines connecting them together, like a private T1 line that ties your offices together, they probably have an internet connection too, so people can surf the internet from the office. You can have web servers at your office that people are accessing from the internet and all of that. So the whole concept of a VPN is, since we're all connected to this big network, why not use this big network, aka the internet, to allow all of our offices to talk together? So let's say this router over here represents an office in Arizona with 100 users connected to a LAN. This is an office in Florida. Now, if we were to purchase a, we'll say, T1 line, a private lease line between those offices, we would have to go to a service provider in Arizona, and that would have to be a service provider that is somehow linked to Florida over there. And we would say, okay, we need a private line between these offices, and they would say, oof, private line. It's going to cost you $2,000 a month. $2,000 in a month, you say, as you throw your pen down on the table and stare at them angrily. Yes, that is, a typical price of what it would cost if you're just going to get a private line between your offices. $2,000. Now, we have these links to the internet, which are, they can be expensive, but I would say overall they're a dime a dozen. In Arizona, maybe for a 100-person office, you might pay for a pretty decent internet speed. I mean, a T1 is about 1.544 megabits per second. And in Arizona, for, we'll say, a 2 to 3 megabit per second connection speed, a business class connection, you might be paying in the range of, we'll say, $300 to $500 a month. Now, that's a business class connection. I know some of you home users are like, hey, I can get internet at home faster than that for, $60 a month. Well, that's a home connection. So we'll say for business class, $200 to $300 there, $300 to $500 and $300 to $500 here. You not only get access to the internet, which you would need anyway, right? But you can also create a VPN connection through the internet, a virtual private network that links the Arizona and Florida offices and not pay a penny more. That's my number one benefit for VPN connections, is that they are cheaper. They are also widely available. They're available anywhere the internet is available. Now, I'm talking right there of one type of VPN that links offices together, but there's another type where we could have our users tie in from home using a VPN connection, and they are, it's as if we bought a private line for that PC or that home to link into the Arizona office. It's available anywhere the internet connection is available. So even that $60 a month internet connection can be used to allow that users to perform anything from home that they could as if they were actually in the Arizona office. It's VPN technology that has really led to the rise of telecommuting. People that work from home full time and do not leave their home, but their home is also their office. Leads to happier employees because, man, you get to save the drive, the gas, the sitting in the office space that you don't really want to sit in, and it saves the company money because they don't have to build a cubicle, they don't have to provide, more restrooms and more break rooms and all those services they have to provide to the employees on site. So it's a win-win situation for most people. Heavily encrypted and secured is the next thing. VPNs, the reason it's called virtual private network is because it's private, and that privacy comes from the massive amount of encryption and security that's thrown on there. Therein is the benefit of VPN, is it's very, very difficult to break into that. It's, I won't say anything's impossible, but it is virtually impossible to break into a VPN connection from the internet. But therein, that third bullet point, is its weakness as well, in that because it is so heavily secured and encrypted, it takes a lot more overhead on the routers than just connecting on a private line. On a private line, you don't have to encrypt anything. You can just let them talk as if they were directly connected because it's private. But on the internet, there's a lot of overhead, a lot of slowdown and processor utilization has to take place there. Last but not least, the big benefit is many-to-many connections. For instance, if I was in Arizona and Florida, to get a private line, it's $2,000 a month, we'll say, and that price can vary, but you can only connect from Arizona to Florida. If Florida wanted to connect over here to California, I would have to buy another private line. And, either Arizona would have to link to California or Florida would have to link to California, and that's another $2,000 a month because that's another private line. With VPNs, all you do is buy an internet connection in each location, and that allows anybody to connect to anybody, many-to-many connections. Remote users can then get into the California office. The site-to-site users, the Arizona to California, they can all connect. So VPN is truly an any-to-any connectivity. VPN connections come in two major styles: site-to-site, or what you see here as L2L, LAN-to-LAN, or remote access. Now this picture right here is a site-to-site VPN connection. This router represents some office that is connected to the internet through some kind of connection. Now you could have inside of that office any number of users, hundreds or even thousands of users, and whenever they access an IP address that is over at this site with however many users inside of it, the router recognizes that needs to go across the VPN. So it will come in clear text, unprotected, unencrypted. As soon as it realizes it's going across the VPN, it will encrypt it and send it through the internet, which is a public network. It's very unsecure. Anybody can get that data, but it's so heavily encrypted that nobody can get to it. It reaches the other end, which unencrypts the data, and then sends it over here to the client. That is a site-to-site VPN, and that is a direct replacement for a private line, something you're paying a lot of monthly charges for. If the site-to-site or LAN-to-LAN VPN links our offices, remote access VPNs link our homes or our laptops, depending on where we are in the world. A remote access client is usually, not always, but usually installed on a PC. You'll, for instance, go to the Cisco website and download the Cisco VPN client, or Microsoft has a VPN client built in. You'll type all the information into that VPN client that's needed to authenticate or work for this central site. It's username and password, or there's many different ways that they can have this. Some companies, I don't know if you've seen these, have token cards, which means somebody to get on the VPN pulls a token out of their wallet. It looks like a credit card, but it has a little electronic screen. They push a button on there, and it generates a password that will let them connect to the VPN for exactly 1 minute. If they don't type that password in 1 minute, they have to hit the button again and get a new password because it's always changing based on time. That's pretty secure. So people don't actually have a password. They have a token card that generates a password for them for that time. They even have biometric methods nowadays where people will have to, I don't know if you've seen them. I've seen them. I want one. They're awesome. I don't know why I want one, but they're awesome. They're laptops that have thumbprint scanners on them, to where to get on the VPN, you actually have to stick your thumb on the laptop. It scans to make sure that you are who you say you are. I mean, I'm thinking, I don't know, you've seen Mission Impossible where they're lopping people's thumbs off and using them on the doors. It's coming, I'm telling you. They have retina scanners where they'll scan your eyeball and weird and creepy stuff. So whatever method they have, you'll authenticate. It goes across the internet to the router, and that allows that PC to become one with the LAN. It's virtually as if that PC was connected to that network for however long they're connected to the VPN. As soon as they sever that, they are now off on the internet again. Everything that they send is encrypted over the VPN. Now, I would say the most advancement has been taking place in the remote access VPN arena in recent years. Site-to-site VPNs, they work, they're standard, they've been around for a long time. Remote access has really been evolving. Before recently, we would always have to, purchase or buy that Cisco VPN client and install it on here. Nowadays, they are setting up people's homes with little routers that make the VPN for you. So you don't actually have to install anything on the laptop. You have this little router at home that will almost create a site-to-site style of VPN from your home to the corporate office. And that allows any device in your home to access the VPN for a time, or however long that's connected. The reason that's pretty cool is because now people can connect telephones, voice over IP phones, to the network in their home, and they could actually have their work extension, we'll say extension 1003, sitting in their office that goes through the VPN, and it's like having a telephone at the work site, but it's at their home. People are dialing 1003 and going over a VPN and making somebody's home phone ring, and they never know that because it's through the VPN. It's invisible. They also have a new technology in the remote access arena that is being called two names, either an SSL VPN or a web VPN. These are two names for the same thing. Installing the clients on the PC is painful, meaning you as an administrator have to go to that person's laptop, get them set up, get them with the token card if you're using that, or retina scanner, whatever you're using, get them all tweaked out, and then they'll be able to go and authenticate. That's fine when you got 1 to 5 users, kind of thing, but when you've got 50 or 60 users that need to access the VPN, that's a lot of time. So what SSL and web VPNs do is they allow this router to generate a web page. Somebody will open their PC and connect to the router, and it will display this web page, and it will say, type in your username and password. It'll have a field on there, or your token code for the minute that it's valid. You type it in there, and what will happen is the router will install a it's like a mini-me version of the VPN client on your laptop for as long as you are connected to that VPN. And that will establish a VPN connection without ever having to install a client on the laptop or the PC. It's pretty awesome. And as soon as you close that page, VPN closes down and everything's eliminated. It actually tunnels all that information through that web page. Some people call that SSL tunneling. But that's where remote access connections are evolving to. That's the logical connections of how VPNs work. Now let's get a little bit technical and into the protocols that give them the power to do what they do. Just about everything that deals with VPN technology is worked all around this protocol known as IPsec. IPsec is the protocol that makes VPNs possible. It is the security protocol that does all the heavy encryption and so on. Now, IPsec works with TCP/IP. We know what TCP/IP is. It's the protocol of communication. It lets you talk over the network. You've got things like TCP and UDP. IPsec is just another one of those protocols. It actually works at the transport layer. Like TCP and UDP, you have a choice. Your computer or your VPN can also choose to use IPsec when communicating over a TCP/IP network. And IPsec is not just one protocol. Just like when you say TCP/IP, there's many protocols that make that work, like UDP and ARP and all these different protocols. IPsec is the same way. Inside of it, it has all these different, what I call chunks, the chunks that build IPsec. IPsec is built of four major categories of protocols. The first, well, I'll take them out of order, is an encryption protocol. You get to choose one of those, and you can see the three in the list, encryption protocols to secure your data. And that is a list from strongest to weakest. From weakest to strongest. This is the weakest, DES, one of the first encryption protocols to come out. Triple DES is essentially triple the strength of DES, and AES is the new U.S. government standard that is the most powerful encryption that we have currently, and that excludes, all of the, under the cover Men in Black style encryption that, nobody really knows about or is proprietary and things like that. The benefit, I guess, is the weaker your encryption, the less processing it takes, and the overall faster connection you have. The stronger your encryption, the more secure you are, the less chance you have of somebody breaking your VPN and getting into your organization, but the more overhead you have and the longer it takes to do that encryption. So, as an administrator, when you set up your VPN, you get to choose what kind of encryption to use. Authentication is the second piece. Authentication does a lot of things, but primarily is focused around making sure data does not change from one end to the other. For example, if you have a client that is connected to a VPN, here's our internet, and is connected to a router that connects to the corporate network, and there's a server. When somebody is trying to hack your network, they may not understand all those packets that are going across because they're all encrypted. So they can't really see what they are. But what they could do, let's say we've got an intruder here. Remember, the internet's a public network, so anybody can get on. We have this intruder who may not understand what you're sending, but what they can do is spoof packets, meaning send fake packets that look like you, that kind of pretend to be you, but aren't really you. This is known as a man-in-the-middle, a MIM, a man-in-the-middle attack, where he's in the middle of the conversation, kind of taking packets and pretending to be you and trying to decrypt the packets as it goes, trying to break into that connection. And what authentication does is prevent those kind of attacks. So authentication makes sure that the stuff that is being sent is from the original person sending it. And it detects if somebody changes your packets. Like as it's going across, maybe he grabs your packet and sends his own in place of it to try and pretend to be you and inject some stuff into the network that doesn't belong there. Well, that's what authentication stops. Now, protection, I'll talk about that one third. The third chunk is what allows you to do all of this over a public network. Here's a thought you may not have thought through yet. If this guy is encrypting, then he has to have an encryption key, right? I'll draw it like this. An encryption formula that allows him to scramble the data before he sends it. Now, in order for this to work, this guy over here has to have the same encryption key, meaning he has to be able to unencrypt what you're sending him in order for it to be of any use at all. So when that PC connects to the VPN, somehow it has to get the encryption key it's going to use over to the router. Or vice versa, the router would have to send the encryption key that it's going to use to the PC. Therein lies the problem. How do you send an encryption key over the internet to this person so that they can have it without this XX guy over here, the man in the middle, grabbing that key, because the internet's a public place. You can grab just about anything you want off of it without this guy grabbing that key and then having the encryption and decryption formula and breaking into the VPN that way. Well, that's what protection is all about. Diffie-Hellman is what that DH stands for, and I'm going to talk about the specifics of how this is possible next. The fourth chunk of IPsec is, I guess, what you could call the engine. The idea behind IPsec is they never wanted it to become outdated, meaning new stuff comes out all the time. New encryption formulas are released. I mean, DES, you see it right there under the encryption. When this originally came out, it was back in probably the late 70s, early 80s. That was like, oh, you are not breaking this. This is unbreakable. Nobody can mess with this. And this is the encryption formula that will end encryption formulas. We thought that was it. And then a 12-year-old girl in Sweden, I'm not making this up, broke that encryption formula. A 12-year-old girl figured out how to break the encryption formula that DES uses in a day. I think it was like within 24 hours or less using her formula. You could break in and pretty much tear that thing to shreds. 12-year-old girl. Unbelievable. She's now dead. The government got her. No, I don't know what happened to her. She's probably working for the CIA somewhere. But that's the idea. Encryption formulas change. AES just came out. It's fairly new. And everyone's like, oh, that thing's so powerful. But give it 20 years and, 10 years at the rate things are going. And that'll be, people will be like, oh, yeah, some 2-year-old in Massachusetts totally tore that thing apart. It's always going to change is my point. So what this negotiation protocol is there to do is be kind of a changer, I guess. That's a horrible way to describe it, but it's essentially a piece of IPsec that lets everything in IPsec be changeable. Think about it this way. If IPsec were a car, this would be the engine of it. And you can actually change out the whole engine of IPsec. If you had a 4-cylinder, you could go out and swap it and put in an 8-cylinder. That's what this AH, ESP, and ESP plus AH is. AH was the original engine that came out with IPsec. The problem is that AH, or it's known as the authentication header, couldn't do encryption. That was back when IPsec was just in its infancy. And so they came out with ESP. Think of that like the V6 engine for the IPsec protocol. And that allowed it to do encryption and authentication and the protection, the chunks that you see on there. ESP plus AH came out, which allows you to double up on things. And that's like the V8 engine. It's more powerful but sucks more gas. It's kind of a resource-consuming chunk. And they can come out with new engines. Someday down the road they'll come out with J59 or something as a new engine of IPsec that adds even more protection. That's the goal, is they don't want it to change. When you think about TCP/IP, we currently use version 4. But the problem is they're having to replace it. TCP/IP version 4 reached its max. It got maxed out, if you will. The IP addresses ran out. So TCP/IP version 6 is coming to replace it. They never wanted to have to do that with IPsec. All right, the last piece of VPN technology that we'll talk about here is how does it all work? I mean, how is it possible to get true security over a public network when you have to send those encryption keys to each other where anybody could grab them? Well, here's the idea. The way VPNs work is through a combination of security keys. First and foremost, I need to identify a big difference in technology. There are really two types of encryption and decryption. First, I'll talk about symmetric. Symmetric encryption is encryption that uses the same key to encrypt and decrypt. Meaning, if you've got that key, it's known as a shared secret key. You can take data, say somebody over here sends some data into the router. You can take that and encrypt it, and then when it gets over here to the internet, shoo, boom, and is received at the other side, they can use the same exact key that you used to decrypt it. The benefit of symmetric encryption is it's really fast and it's really easy on your processor. When we talked about DES and triple DES, 3DES, and AES, those are all forms of symmetric encryption, meaning they use the same key to encrypt and decrypt. Now, that's great, and it's very fast, but the problem is one of these routers is going to generate that key every single time somebody connects to the VPN, and it has to send it over the internet to the other side, so they've got that key to do the encryption and decryption. That's the problem I described before. So how do you do that without somebody grabbing that key in the middle and then using that to tear apart all your VPN, and they can decrypt anything that you send? That's where Diffie-Hellman came in. Diffie-Hellman is actually the name of two guys that created a system for doing this. Diffie and Hellman actually work together. And here's the idea. Diffie-Hellman security uses something known as asymmetric encryption. What that means is you have a two-key system, a public and private. The public key, anything that it encrypts, can be decrypted with the private key. And anything the private key encrypts can be decrypted with the public key. They can do both, but they are complete opposites of each other. Now, they're called public and private key for a reason. When somebody connects to the VPN, let's say this is a site-to-site. I'll put S2S, site-to-site VPN between these two routers. When somebody brings up that VPN connection, the first thing that happens is the router that receives the connection sends a key. Let's say that the right router connected to the left router. The left router will send the right router its Diffie-Hellman public key. Check out that animation, pretty sophisticated. So now this right router has an encryption formula. Anything encrypted with this public key can only be decrypted with the private key. Now, there's the secret. That private key is kept hidden behind this router or in that router. It will never be given out to anybody. That's why they call it a private key. So the router on the right generates that shared secret key and encrypts it with this public key. It's like encrypted. So it sends this encrypted version of the shared secret key, trekking across the internet here, over here, and that is completely scrambled, and the only thing that can decrypt that is the private key. Likewise, if we were to connect the other way, the right router would send its public key over here, and then its private key would be used to decrypt anything that the left router encrypted. But we're only using one set for now, so let me move these out of here so we're not confusing. Once this router on the left-hand side has the shared secret key right here, it's able to decrypt it with private, and then they both have the same symmetric encryption and decryption key that they can use for that session. Now, once that VPN connection is done and over with, meaning, okay, we're ready to tear it down, that shared secret is thrown away. Off it goes. And the next time the connection happens, a new shared secret key is going to be generated. So the point is that the encryption keys that are being used to encrypt all the data over the VPN are constantly changing. They're always being regenerated and renewed. Even if this is a site-to-site VPN connection that's always connected, it's always up, always on, after a certain amount of time, it will say, okay, we've used these keys long enough, let's scrap them and regenerate them again, and then use these Diffie-Hellman keys to secure the exchange of that shared secret. Now, you might be thinking, couple thoughts I had when I first got into cryptography and how all this works. You might be thinking, well, first off, if you've got this encryption formula right here, Diffie-Hellman public, and you're sending that all over the place, meaning that's being sent in clear text across the internet, can't somebody get that key and, kind of reverse the formula to figure out the private? I mean, the way I was thinking about it, I thought, I took algebra, I even took calculus, If the Diffie-Hellman public key is x plus 1 equals 2, I can do the math, subtract it out, and be like, oh, well then X really equals 1. Now I've got the secret. Well, you can tell the brilliance of my mathematics. I'm like, that's difficult right there. But the public keys and the formulas that they use in those Diffie-Hellman public keys are so sophisticated and so advanced, it is theoretically impossible to figure out what the reverse encryption of that is, or what the reverse of it is, if you just have one side of the key. Meaning inside of there, they use logarithmic functions and things that just cannot be reversed. There's a billion possible answers to what the reverse of that could be. So, you'll just have to trust me if that doesn't all make sense. It is impossible to create or reverse engineer a private key if you just have the public key. Second thought I had when I first was learning about this. If the public key and private key system is so super duper secure, why do you even need this shared secret thing? I mean, why can't you just get these shared secrets out of here, reduce some of the complexity, right? And just say, okay, we'll just use the public, and I'll send you my public, and you'll send me your public, and then I'll use this to encrypt everything, and you can decrypt it with your private, and you can use, let me put these keys in the right place. You can encrypt anything you need to send me with your public, and I'll decrypt it with my private, then kind of swap it that way. Well, honestly, that would work, and that it would secure, but these formulas, it kind of goes along with the last answer I gave you, these formulas are so massive and so super complex that they cause a ton of overhead. Asymmetric is like 100 times more processing than what a symmetric key would be. It really burdens down your router, and that's why the routers only use them for an instant. They just use that encryption formula and that system to get the symmetric key across, and then it says, okay, I'm done with you because you max out my processor. Otherwise, that would be the perfect encryption solution. That's the idea behind VPN connections, at least at the CCNA level. I encourage you, if you want to know more about VPNs, Cisco has now added it to the CCNP track. It's actually in the CCNP now under the ISCW exam. So if you want to check out CBT Nuggets, they offer that video. And also, if you want the full scoop, the ISCW gives you much more than what I just gave you. It's about 8 videos on it. But if you want the full scoop on what VPNs are, how to set them up, how to work with them, all that, that's what the CCSP track is all about, the security track for, did I say CCSP? I think I did. CCSP, the security track for Cisco. That's where they talk fully about them. In here, we talk about why to use VPN connections. And to review, we use VPN connections because they're cheaper. They allow more flexibility. You can connect to more places, and you can just use your existing internet connection to make that happen. They're very flexible. We looked at the different styles of VPN connections, which was really divided into site-to-site and remote access VPNs, where remote access is seeing the most evolution right now as we move into technologies like web VPNs. Finally, we looked at a high-level overview of VPN connectivity, talked about the IPsec protocol suite that allows VPNs to happen, and how IPsec and how